All right, so we're now moving on to the next section, and that's section C, which is function notation. There's quite a bit that we want to talk about in this video, so I'm going to go through this introduction just a little bit faster than normal and hope that we can keep this video shorter. But what you need to know by the end of this video, or by the end of this section, is how to write a function in function notation. You'll need to know how to substitute for a variable in function notation and how we represent that. You have to know how to solve problems using function notation. We're going to know how to do what's called composite functions. And then last but not least is we will then be given a graph and you'll have to describe and talk about the changes of that graph to its parent function. So there's quite a few things that we need to know in this video. None of it is really that hard. The hardest part is probably this composite function, but as long as if you can understand how to substitute in for a variable, it's essentially the same thing. All right, so let's go ahead and get started by first talking about function notation, and then we'll work our way through these learning objectives. All right, so first let's talk about function notation and how we write this. If I give you this equation, y is equal to 3x plus 4, we should know that this is a linear equation because our variable has a power of just 1. So we know that this is actually going to form a function because if we draw a straight line, it will pass the vertical line test. I also just drew a quick little sketch for you off to the side here. This is what this graph would look like. And you see, if we were to draw a vertical line test, this does pass it. There's no point where we would have this one x value that generates two different y values. So we know that this is a function. So to let the reader know, or to let people know that this is a function without having to do anything with it, we represent it by using this notation of f of x is equal to 3x plus 4. So we replace the y with this f of x. And, and this tells us that this is a function. Now, it doesn't need to be f of x. It could be g of x is equal to 3x plus 4. It could be h of x. So there's any letter that we use in front of this can represent the function. It just is going to be written with that variable x in parentheses. And the variable that gets written in this parentheses must match the variable of the original equation. So for instance, it doesn't have to be x either. If you guys are doing a word problem and you're creating a word problem and you're creating your own variables, and let's say that we use time and you wanted to use t for time instead, so we could then say that f of t is equal to 3t plus 4. So you see, whatever variable we have inside this parentheses is matching the variable that we have for our domain and how we're representing that. So the letter out front that we use, this f of x or g of x or h of x, we can use any letter we want to represent the function. You'll see these are usually the ones that you'll see used the most, this f of x, this g of x, and this h of x. But also the same thing is we can represent it with any variable as well. So if we're creating our own variable and we're using t, just whatever variable is inside of this is the variable that we need to make sure is part of our equation. All right, so this is how we represent it. And once we see something written like this, we know it's a function. We know that every single x value that we substitute in, or every domain that we substitute in, will give us one range in return. We know that it will pass the vertical line test. So it's allowing us to know right off the bat, without needing to do anything, that this is a function. All right, so that is how we represent it with function notation. Now I'm going to erase this and I'm going to show you how we can substitute in for a variable when using function notation. All right, so now if we're given a function f of x is equal to 3x plus 4, and I ask you to solve for a function when x is equal to 3, well, if we had y is equal to 3x plus 4, you know that, okay, well, we substitute in 3 for x, so now we have 3 here, and then we can go ahead and solve and say, well, y is then equal to 13. So before, that's how we would do it. Y is this equal to 13, and we just simply substitute in. When we're using function notation, when we substitute, you do need to make sure that you rewrite this to show what we're plugging in. So instead of it just saying f of x, we will say f of 3 is equal to 3 times 3 plus 4. So you see, by writing this 3 here, this is telling us what we're substituting in for our variable x. So it's allowing the reader know, okay, we're looking at what the value is when x is 3. And then we would say, well, f of 3 is equal to 13. So it's exactly like we did here, but now we just need to replace that x with the number that we're substituting. And we can still generate this as an ordered pair because we know that we would substitute it 3 in for x. So this gives us the ordered pair of 3, 13. So it really doesn't change anything from what we were doing before. It just allows for us to now write it in a different notation so that we know that it's a function. And then when we are substituting in, it's telling us that whatever this variable is here, this is what we're substituting in. And this is something that's really important when we get to composite functions in just a moment, because if you can understand that what we're substituting in for a variable simply just gets written in this part of our parentheses to represent, hey, that variable is no longer there, we're substituting 3 for it, and we actually substitute it in to our actual equation. Well, when we get to composite functions, it may look hard, but it's actually the same thought process, the same thing, and it's not really that bad. All right, so when we substitute, instead of just saying x is equal to 3 like we did before, we then will fill it in inside of our function notation to show, hey, we substituted this variable x with this number 3. And then it tells us when our function is 3, our y value typically, or our output is 13, and allows for us to easily create this ordered pair. All right, so now we just did a problem where we were substituting in for x. But sometimes, as we've done throughout this year, is sometimes we will solve for x instead. So maybe we say, okay, well, we know y was equal to 22, so what was x values for this? We can still do that for this. So sometimes we don't need to say, okay, we're not substituting in for x. It might be written as f of x is equal to, let's say, 19. So in this case, you see we aren't substituting anything for x. X is still written as the variable, and we're just saying that f of x, the function, is 19. So that means wherever we see this f of x, we're substituting 19 in for it. So if it's written like this, we would say 19 is equal to 3x plus 4, and now we're trying to solve for, well, what x value generated our function, our output of 19, and we solve it just like we would a regular equation. So now 15 is equal to 3x, we divide by 3, and that means x is equal to 5. So that meant that when x was 5, our function was 19. So we can say f of 5 is equal to 19. Or we can write the ordered pair as 5, 19, right? But if it just says f of x is equal to 19, that means that we're substituting for the entire function of what it was equal to, and we're not just substituting in for the variable. All right, so now that we explained this, we're going to do 2 examples, one of each again, just to make sure that we understand what we're doing with this. All right, so for this problem, it says evaluate the function f of x, evaluate the f of x equals negative 4x plus 7 when x is equal to 2. So they're telling us we want to substitute 2 in for x. So now we will then say, well, f of 2 is equal to negative 4 times 2, because we're substituting 2 in for x, plus 7. Well, f of 2 is then equal to negative 4 times 2 is negative 8 plus 7. And f of 2 is then equal to negative 1. Right, so we can say when x is equal to 2, f of x is equal to negative 1. That's a long way of writing if you wanted to. You can say that we have 2, negative 1, because it's telling us our input and our output. So either way, you can just write it like this, and you'll get full credit for that. This is another way that you can write it as well if you want to be a little bit more explicit and a little bit more detailed in your response. But writing it like this shows me that you know that we're substituting in for our x and solving for our function output. All right, now let's do the next example. All right, now the second example says f of x is equal to 6x plus 9, and now it just says f of x is equal to 21. So since they're not telling us that x is equal to something, and we're not asked to substitute in for x, they're telling us what the whole function is equal to. Well, we need to substitute that in for this f of x. So instead of it saying f of x is equal to 6x plus 9, we now know that the output that we're looking at is 21, and we're trying to figure out, well, what input gave us that output? So now we just set it equal to 21, and now we're going to solve like a normal equation. Well, 21 minus 9 is 12. So 12 is equal to 6x, divide by 6, so x is then equal to 2. All right, so once again, we can write it as just x is equal to 2 in this case, because we're just trying to solve for what x is. Or if you wanted to write it as an ordered pair, that would be fine as well with me. But this is all you need to do for this one, because we're just asked to solve for x when our function is 21. All right, so those are the first 2 learning objectives. So now let's move on to the next ones. Actually, those are the first 3 objectives, because we talked about what function notation looks like. We substituted in for a variable, which was the second objective, and this was our learning objectives, our third learning objective, where we were solving problems when given the output of the function. So we've just gone through the first 3 objectives, and now we're going to move on to the fourth one, which I think might be the hardest part of this video. But as long as if you understand that whatever is written in replace of this x gets substituted in for x, it really isn't too bad. All right, so before we go into this stuff on the right-hand side that may look very complicated, let's just go again with substitution so we can understand how this applies to what we're going to do here. So if we have f of x is equal to 2x minus 1, and I tell you x is equal to 5, well, we are substituting that 5 in for x, and we know that we're just substituting that 5 in for x in our equation as well, and we're just solving. So whatever gets written here gets substituted in for the x in our function. So I'm going to show you real quick before we go over the definition and do a couple more problems of this, of what this is called a composite function. And you see, instead of it just being a number that we're substituting here, we have two functions. F of x is equal to 3x, and g of x is equal to 2x plus 1. This is asking us to find f of g of x. That's how we read that, f of g of x. So instead of our typical x that we have written here, we're now going to substitute it with our g of x function. So that means this is going to be substituted in for our x. So we can write f of g of x is equal to 3 times our variable x, but we're now replacing it with our g of x function, which is 2x plus 1. So now it becomes 2x plus 1 because where our x was, we are now replacing it with our g of x function. So now we would just simplify this and say, okay, well, 3 times 2x plus 1, so f of g of x is now equal to 3 times 2x, which is 6x, and 3 times 1, which is 3. So you see, if you understand that whatever gets replaced with that x inside this notation is just gets written there in the actual equation or function itself, then you understand this should be a little bit, it should make sense to as well, because instead of writing just our regular variable x, we're replacing it with our g of x function, which we know is equal to 2x plus 1. So where we had our x in this original f function now needs to be replaced with 2x plus 1 because we're replacing it with our g of x function. And then we just need to simplify like we always will with math, where we're simplifying, distributing, and this then generates the function of 6x plus 3. All right, and this is called a composite function. So now I'm going to show you the definition, and we'll do a couple more examples, maybe one or two, and then that will be it for that fourth learning objective before we move on to the fifth and final. All right, so a composite function is a function made up of other functions. And another thing that we can think about it is where the output of one function is the input of another function. Now, I'm going to explain that at the end of this question. All right, but the questions may appear like this, where you have f of x is equal to 5x minus 1, g of x is equal to 2x plus 3. So we have our two functions. Now we're asked to find f of g of x. So instead of f of x, we're now substituting our g of x function in for that x value. So we would then have f of g of x is equal to 5 times x, but instead of it being x now, we're substituting with our g of x function, so it's the entire 2x plus 3. And since it's 5 times x, make sure that you are putting this 2x plus 3 in parentheses, so that way we know to distribute the 5 to all of it. And then we still have that minus 1 at the end of that problem. So now we'll simplify. Well, 5 times 2x, now I have f of g of x is equal to 10x, because that's 5 times 2x, times 5 times 3 is now plus 15, and we still have that minus 1. So our final simplified version of this composite function is 10x plus 14. All right, so we can then just substitute it in and simplify to get that composite function. Now, what they mean by this output of one function is the input of another. Let's say I asked you to do this instead. So if I said, not only do I want that composite function, but let's find f of g of 2. All right, so one way that we can do this is we could find the composite function, and then once we get that, we can just substitute it in. So f of g of 2, because now I'm substituting 2 in for the x here, which means I have to substitute 2 in for this x, it becomes 10 times 2 plus 14. So f of g of 2 is now equal to 20 plus 14, or f of g of 2 is now equal to 34. So we can then solve for what that is there. Now, what they mean by the output of one function is the input of the other is what we could do is I'm going to erase this over here. So this way we have room. All right, so what we could do is instead of doing this composite function like this, if I'm asked to find f of g of 2, what I could do first is start with this inside function, which is g of x, and I'm going to substitute 2 in for that g of x. So now I'm finding g of 2 is equal to 2 times 2 plus 3. So g of 2 is equal to 4 plus 3, or g of 2 is equal to 7. Now, since we know what g of 2 is equal to, instead of writing it as g of 2, I can then say, okay, I'm going to take this output of that first function, and since it was inside of our f of x, I'm then going to substitute that in for our f of x function. So now I can say, well, f of 7, because this g of 2 I know is equal to 7, so because g of 2 is equal to 7, so I can then replace g of 2 with that, is then equal to 5 times 7 minus 1, because I'm substituting this answer in to my function, my f function. So f of 7 is now equal to 35 minus 1, and f of 7 is then equal to 34. So you see, no matter how we did it, we still got the same answer. So you could, if you're given a problem like this, you could find the composite function first if that is something that you find easy, and then you can substitute the 2 value in. Or if that is something you're having trouble with, what you could do is isolate or take that inside function first and actually solve for it like we did here. And then once you see what that g of 2 is equal to, we can then replace that g of 2 with our answer and then solve from there. You see, it gives us the same answer both ways. All right, so that is our fourth part of this video, which is our composite function. And now the last one is just going to be comparing graphs to our parent function. All right, so now we're going to have to know what a parent function is first before we can talk about anything being done to it. So what is a parent function? A parent function is the simplest version of any given function. So of that function, of any given function, without any computations being done to it. That means no multiplication, no division, no powers, no addition or subtraction. So we are learning linear functions. We've already done that. So that means the most basic and parent function of a linear function is simply f of x is equal to x. If we were to graph this, we would have a straight line with a slope of 1, and we would have the y-intercept of 0, so it's passing through our origin, which all of our parent functions do pass through the origin, so that point 0, 0, and it's with nothing being done to it. So the other parent functions that you'll learn in the future, not this year or maybe later this year, are quadratics, so it's just x squared. Our next one that you might have is this x cubed, so it's our cubic function, and so on and so forth. So all these are different functions that we have, and they're our parent function, which is our most basic version of these types. And when we talk about translations or things happening to our graphs, we always are comparing it back to this parent function. All right, so now we're going to go through and just talk about some examples and how we can describe what's happening. All right, so we're going to keep this pretty basic for right now. And we're always going to, if I ask you to compare anything for right now, it's going to be compared to the same slope. We'll talk about maybe in the future this year, but you guys will learn what happens, how we describe when we are multiplying that at x. But for right now, we're going to just compare it to this parent function of y is equal to x. So this red graph is here. So that's our parent function. You see it passes through the origin, 0, 0, has a slope of 1. Nothing's being done to it at all. So now this blue graph, we are just doing y is equal to x plus 4. So it has the same slope. So if I do give you a problem that does have maybe 3x, and I'm asking you to compare it to 3x, the slopes will be the same for now. But if you notice, from this origin, all it does is move up 4. So every single point I pick on this graph, if I were to see what happens, it moves up 4 every single time. So when we have this, we would then, all we need to say is that from the parent function, it has a translation of 4 units up, that it's moving 4 units up every single time. So if we were to plug in f of 0 for both of them, we'll see that the blue graph is giving us an answer that is 4 more. If I plug in -2, we see that our blue graph is just giving us an answer that is 4 more as well. So it's just telling us that our graph has a translation, or it moves up 4 units. And the same thing for this one. If we look at the green one, well, from our parent function, everything just moves down 3 units because it says we're minusing 3 from it. So it kind of makes sense. So this tells us that we're moving down 3 units. All right, we have a translation that we're moving down 3 units. Here we would say we move up 4 units. So as long as if our slopes are the same, which for right now they're going to be, and if they're not, we'll discuss that. But for now, we're going to keep our slopes to be the same. And all we do is just look to see, okay, well, what are we adding or subtracting to it? And then that just tells us how our graph is moving up or down. And we would say that our parent function moves up 4 units. Our parent function moves down 3 units. And that's all that we would need to do to describe the translation or the effect of the new graph to our parent. All right, and that is it for this video. I know it's a little bit longer, but there's quite a few objectives that we needed to do for this.